Thank you. Thanks for the introduction, and thank the organizers for the invitation. It's a great pleasure to be back here at CM again after 7 years for the same conference. So today I'll report a joint work with Shouwu Zhang about the generic positivity of the Beilinson-Bloch height, and I will present one systematic result, the first result we have, but it's a new project and there are a lot of open problems that I will explain in the last slide. So first of all, I want to start with something simple. I guess most of you know what height function is, but still let me repeat a little bit more. So height function was introduced by André Weil in his PhD thesis, and the goal is to measure the size of algebraic numbers or rational numbers or algebraic numbers. So for a rational number a over b, this height is just a log of max of the numerator and the denominator, take the absolute value. And the definition generalizes to any algebraic number by this formula. Because of that, we can define the height of any algebraic points on projective space. And this height defined like this is called the logarithmic weight height and denoted by small h. I prefer the log version because product is too complicated for me. I like to do sums, okay? And if you define a height like this, of course, you need to check that it's well defined. It doesn't depend on the choice of the coordinates and so on, but this is true by the product formula. And there are two important properties. Neither of them is hard to prove, but they are very important. The first one is this height is always non-negative. And we know which points have height 0. They correspond to the points where all the coordinates are either 0 or roots of unity, as explained in Gabriel's talk. Now, another important property is this Northcott. So there are only finitely many points with bounded height and bounded degree. So again, the proof itself is not hard, but many finiteness results in Diophantine geometry boils down to this fact. So it's very important, and these two important properties, they are the things that we're going to study for logarithmic weight height. And next, we have this height for any projective variety. So given any projective variety, we can put it in Pn so that we can compose with this logarithmic height to have the so-called naive height. But we have more than one way to embed it. It depends on the choice of a line mono and the choice of global sections and so on. So if we have different choices, we have different height functions, but they differ always from a bounded one. So they still have these two nice properties, but at this stage, it doesn't make sense to talk about positivity. We say that this height is bounded from below. It has a lower bound. For Northcott property, it's still the Northcott property. And next, let's make it into some abstract thing. So let's talk about a quasi-projective variety. Pay attention, here is a quasi-projective variety defined over a number field. And let's take any function from the set of algebraic points to R, any function. And we call this function a dominant height or weight height if, first of all, it has a lower bound, and secondly, it satisfies the Northcott property. It would just make its name of dominant height. And here are two examples I want to present. Apart from the weight height on Pn, these two examples are probably the most famous examples. The first one is the normalized Néron-Tate height on abelian varieties. This function is not only just well defined up to a bounded one, it's a genuine function, it's a normalized one, and the lower bound is 0. And we know that the points of height 0 are precisely the torsion points. This height function is used in the proof of Mordell-Weil theorem, or the idea of this height being quadratic is used in Mordell-Weil theorem for high-dimensional abelian varieties. And in some formulation of the BSD conjecture, this height also appears in some formulation. So it's very important, especially for the formulation of BSD conjecture, to have this normalized one, And the second example is the Faltings height. When Faltings introduced this height to prove the Mordell conjecture. And here, let's just talk about curves. So we say that the Faltings height of a curve, it is just the Faltings height of the Jacobian. Okay, and this defines a function on the modulus space of curves. And Faltings proved that this is really a dominant height by comparing it with the weight height. Okay, So all these are functions of varieties, but they are functions on algebraic points of varieties. And we have a natural question to ask, okay, can we extend this function from heights of points to heights of cycles on varieties? And moreover, we sort of want a normalized one to relate to like L functions and zeros of L functions and so on. And this kind of questions was asked by independently by Beilinson and Bloch in the 80s. So they extend the height of points to height of homologically trivial cycles. And this is usually called the Beilinson-Bloch height. It is conditionally defined depending on the existence of some good integral model, but for some cases, it is unconditional in these cases. And then they conjecture the positivity of the Beilinson-Bloch height, and it should be 0 if and only if the cycle is torsion in the Child group, and they conjecture the finiteness of the Child group and a generalized form of the BSD conjecture. So it's related also to some critical values of L functions and so on. And in my talk, I'll focus on the easiest cases where this height is known to be unconditionally defined. So they correspond to, they are constructed using curves. So we start with a curve of genus at least 2, and let's take a canonical divisor of degree 1. So it's the canonical divisor divided by 2g minus 2. Let's take this C. And then we have 2 homologically trivial one cycles. One is called Gross-Schoen cycle, one is Ceresa cycle. Gross-Schoen is defined to be a one cycle on C cube. So we have this cube here. Each direction represents a C, and this 6C is the origin. And then we have all the partial diagonals. We have the full diagonal, which allow the 3 coordinates to change. And we can also fix one coordinate and let the rest change. So we have all the partial diagonals. And the modified cycle, Gross-Schoen cycle, it is the alternating sum of these partial diagonals. So sometimes we call it the modified diagonal. It can be proved that this is homologically trivial. And the other one is Ceresa cycles. It is a one cycle on the Jacobian. So we do the Abel-Jacobi embedding based at this canonical point, and we do is pull back by -1. So we have this red curve and the blue curve both on the Jacobian. And the Ceresa cycle is the difference of them. So the first cycle, Gross-Schoen cycle, is preferred in number theory because it is really related to L functions and the critical values of L functions and so on in a more direct way. Ceresa cycle is preferred by algebraic geometers because if the Ceresa cycle is torsion, it means that we can deform this red curve to the blue curve over P1, continuous over P1. Nevertheless, these 2 cycles, even though they lie in different places, different spaces, actually they share very common properties. Like one is torsion in the Child group if and only if the other one is torsion in the Child group, and their Beilinson-Bloch heights are proportional in a uniform way. Okay, and now finally, after the object, I'm going to say that this goal of the project is to propose a systematic way to study the positivity of the Beilinson-Bloch height and study some torsion behavior. So you see this happy face, it should be positive. And the starting point of this is like many questions in Diophantine geometry, we want to study some object, and we put all of them together on a parametrizing space, and we study things on the parametrizing space. So we will use this Beilinson-Bloch height to define a function on a suitable parametrizing space. And for Gross-Schoen cycles or Ceresa cycles, they define functions on the modular space of curves. So we have the Gross-Schoen height function, the Gross-Schoen function, and the Ceresa function, just using the Beilinson-Bloch height. And some facts. One is both functions vanish on the hyperelliptic locus because you have this point that you can do evolution. And secondly, we have this relation of these 2 heights. So it suffices to study one of them. Just pick up your favorite one. And now we want to study the positivity of these heights, and we're going to divide this question into different grades and try to answer one by one. Can we do that? First of all, we need to assume G to be at least 3, because when G is 2, everything is 0, it's nothing interesting. So when G is at least 3, we want to show that this height is a dominant height. But first of all, because it vanishes on the hyperelliptic locus, it cannot be. The Northcott property will not be satisfied. So the best thing you can imagine is it's dominant on the Zariski open dense subset. And moreover, for these kind of questions, rationalities is really important. We really want this set to be defined over Q, not just Q bar. We really want this set to be defined over Q. So the first question is, can we find such a Zariski open dense subset defined over Q on which this height is dominant? And secondly, can we determine this U? Given any curve, can we decide whether it's in U or not? And third, of course, is this lower bound here non-negative? It is lower bound here non-negative. And our main result now is we are able to answer part 1 of the question completely, and we are able to answer part 2 of the question very partially, but that's it. And unfortunately, still, given any curve, we cannot decide whether it's in this U or not, but at least we have a result saying that, okay, let this we call this MG ample locus to be the maximal Q bar Zariski open subset on which it is on which the GrossSchoen height is a dominant height. Of course, such a maximal one exists by some Noetherian property. Then first of all, part 1 is equivalent to say that this ample locus is non-empty and it's defined over Q bar. And part 2 is we can give a construction which is a construction itself, but it's not going to be very satisfying. In the end, you will see what it is. But at least now we can do a corollary of the Northcott property, fixing any number field. Then we have only finitely many curves which has bound, the height is negative, which has negative height. So this is a generic positivity result. And also for cycles, usually when we study this kind of problem, we do fix a number field. We do fix a number field to study these cycles. Okay, so this is the generic positivity as a corollary of the Northcott property. Okay, the proof of this result, it uses some recent developments in Arklov geometry and Diophantine geometry. We have this arithmetic side where we use the theory of eidetic line bundles, very recent one developed by Yuan and Zhang, and we need to prove some volume identity for which we use Morse inequalities, something is a very analytic proof. And we on the Diophantine side, we study the Betti map, Betti form, Betti strata in this new situation, and we use some functional transcendence result, and compared to like uniform model long, a new input is this O minimality for period map in this case. To link between them, we need to do some Abel-Jacobi periods, and it relies heavily on Haynes' works in the 90s on the Archimedean local heights. So use Hodge theory to study Archimedean local heights, Haynes result. Okay, so let's start. The first theorem I'm gonna show is, okay, there is an eidetic line bundle which defines this height. So it is actually a height function. It is defined by a line bundle. I'm not gonna explain what eidetic line bundle is exactly, but I'm just gonna say that they are matrix line bundle, meaning that it is a line bundle on MG such that for each place of Q, you can assign a metric for this line bundle. So it's a matrix line bundle. It's finite places, infinite places, you have a metric. And this line bundle, it can be approximated. It is the limit of some Hermitian line bundles. And it's in classical Arklov geometry, the Hermitian line, but when we talk about Hermitian line bundles, we talk about them over projective arithmetic varieties. So they should be integral models of compactifications of MG. So here we take all of them and take a limit. So in the end, we do want to have something which is defined over Z and on some integral model and on some compactification, but it doesn't matter which one. It doesn't matter which one. So it is this eidetic line bundle. So such a construction was given by Yuan using some phi graph construction, but in our paper we give a new construction for which we really need to prove this volume identity. And from our construction goals, I give a sketch of this construction, especially the step 1. Step 1 is purely geometric. It is just a Poincare bundle on the universal Jacobian. So you have the universal Jacobian times itself, and then you have a Poincare line bundle. It's defined in this way for the principal polarization. I write it down here to emphasize that if you write down something like this, a priori, you have no reason to see why it is nef, because you have this minus sign. And in fact, this problem of nefness is the hardest thing in our paper. We cannot prove that it is nef. We cannot prove it's nef. So nefness is not known. And the second step is, on this universal Jacobian, we can extend this line bundle to an eidetic line bundle. And this uses heavily the polarized dynamical system. So you have the multiplication by 2 on a abelian variety, and on the family of abelian variety is polarized dynamical system. So this is why our construction is really, really confined to the GrossSchoen cycle. It doesn't work for general family, so far not. Okay, this is why. So the first step, it's important to see this step to see that the nefness is actually a big issue, and the second one is why it only works for this GrossSchoen cycle, and then we do the Deligne pairing to push forward to MG. This is a more general thing. Okay. So this is the construction of our line bundle. By this step, because of this step, it only confines to the Gross-Schoen cycle or something related to abelian varieties. And by the first step, the nefness is not known. It's not trivial at all. And in this theory, in this new theory, even though we don't consider integral models, something happened. Because now we're considering limits of integral models of compactifications of MG. What if we forget about all the integral structures? Then we still have all the compactifications of MG, and we are studying line bundles on one of these compactifications. So still we're doing a limit process. And with this new limit process, easier one, we have the so-called generic fiber of L bar, and we call that L tilde. It's like if you have a line bundle on an integral variety, then you can take its generic fiber. Here we're doing similar thing, except that now everything is still a limit. So we do, in height theory, we do want to work with projected things. But so we want to have some projected compactification. But in practice, often it doesn't matter which one we take. That's the idea. Okay, now this is our theorem. We want to show that the Gross-Schoen height is a dominant height on the Zariski open thing. And in terms of eidetic line bundle, this is equivalent to say that this generic fiber is big, so that you can find a section, then apart from the divisor of this section, it has a lower bound and so on. And next to descend this set to Q, we need to characterize those subvarieties of volume 0. And of course, I haven't explained what the volume is, and this is the next slide, and this is one. In my opinion, this is the hardest theorem in our paper to prove this volume identity. Okay, we show that this volume is precisely as expected. You take the curvature form, you take the top wedge power, and you integrate. So before moving on, let's look at the feature of this one. The volume is still defined as in algebraic geometry. It's the volume of in terms of the growth rate of the global sections. It's just now you require some growth behavior at the infinite at the boundary. But at least it's some kind of H0, so it is invariant under the automorphism of C. And this is why, so on the left-hand side, it's something very algebraic geometry or arithmetic. Okay, it's really defined over Q, so it's invariant under the automorphism of C. On the right-hand side, you have something very complex geometry. So when you apply the automorphism of C, you will get something, and this is how we descend everything to Q in the end. But this volume itself, it looks very much like Hilbert-Samuel or arithmetic Hilbert-Samuel. And in fact, if you can show that L tilde is a Neff line bundle, then this follows immediately from Hilbert-Samuel. But that's the problem. We cannot do it. We cannot do it. So our proof really goes back. We really compute this volume directly by using our construction of this limit process. We really do the limit process. We compute the volume of every term in that limit, and that's where we use Morse inequality to do this volume thing. And again, it's confined to this case related to the abelian varieties because at a certain stage, we need to take the average of torsion points to have fast enough convergence. Otherwise, a priori, it's a weak convergence. But this is probably too much detail. But I just want to say that also in this step, it's confined to this case. Okay, but at least now we do have this volume identity, and with this volume identity, to prove this theorem, we need to do three things. Well, we want some positivity, so we want that this 1-1 form, this curvature form, is semi-positive. And secondly, we want that if we work with the whole mg, then the top wedge power is not identically 0, so that this integral is going to be positive. And third, to descent over Q, we want to show that this top wedge power, it vanishes exactly on the zeriski closed subset. So this is the thing to do. And the third one, I put a quotation mark because it's not exactly this one, but philosophically speaking, is this. So it remains to prove this. Now this is what we wanted to do, and now we're reduced to this one. So we're reduced to prove these three things. And the bridge to them, the first step is to show that, to give another characterization of this curvature form. And in fact, we show that it equals the Betti form. And this also can be deduced from some work of Robin de Jong a long time ago, actually. Although none of these things existed. The C1L bar didn't exist, and the Betti form was not defined in a very explicit way. Okay, and next we go to the geometric part, which works for actually any family. And when I show this, I'm pretty sure that many of you will see that this is something very familiar, you are very familiar with. Okay, now let's go to the geometric part, and let's make some notation for that. So we now have a family of Gross-Schoen cycle or a family of Ceresa cycles. So this is a family of Gross-Schoen cycle, this is a family of Ceresa cycles. But actually we can do it in a more systematic way. Let's just take a family of projective varieties over a quasi-projective variety, and let's just take a family of homologically trivial cycles of codimension n. And both cases fall into this framework. And now with this, now let's look at each point here. Let's look at each fiber here. For each point, we can define the so-called intermediate Jacobian indexed by n, which is just the codimension of these cycles, in the following way. So first of all, the very naive way to see that is just, it's nothing but the integral, the real cohomology mod the integral cohomology. So it is just a real torus of some rank. It is a real torus of some rank. But we can write this real cohomology a little bit better using Hodge theory, because we have the Betti-Duran comparison. It's isomorphic to the complex cohomology mod the middle filtration in Hodge theory. So that if you write down in this way, you see this one has a complex structure. This one has a complex structure. It is a complex torus, which is compact, and it's isomorphic to the real torus in a canonical way. So each fiber is like that. And we know we do have something like that. That's abelian variety. If we have an abelian variety, we can see it as a real torus. We can see it as a complex torus. So this is just a generalization of that without the algebraic structure. Okay? And Griffiths defined the so-called Abel-Jacobi embedding from the homologically trivial cycles of each fiber to this intermediate Jacobian. So in the case of curve into Jacobian, the left-hand side is just P, any point minus your base point. That's homologically trivial. And on the right-hand side, it is the usual Abel-Jacobi embedding. So it's just that. So Griffiths proved this one. And now if we take ZS here on this side, we have a point here in this complex torus or real torus. And again, as in abelian varieties, this can be done in a family way. This can be done in a family way. And this is a family of complex tori, and it's isomorphic to this local system of real tori. And then when you see that, you can define the so-called Betti map and so on. But here I'm going to do it in this new situation. So first of all, we have this homomorphic section which sends each point on the base to the Abel-Jacobi image of this homologically trivial cycle that we had, this Z. So for example, this X is just a CG cross CG cross CG over MG, and this Z is the family of Gross-Schoen cycles. Say is that. And because of this one, we can do like the so-called Betti map in this case. I'm going to write in this way. So it's a tangent space from the base to the tangent of the whole variety, complex variety. And if you look at here, then it just decomposes very naively. And then we project to the second factor. So this is almost just the Betti map in Diophantine geometry which was introduced by Maser and Zanier in studying relative many-manifold conjecture. And later on, Philip used this one to denote the non-generic things, and then we generalized it together to study the uniform model long conjecture with Veselin and Kühne and Ge. And now I'm going to define this Betti form. I'm not going to give an actual definition, but it's just the pullback of some two form here. This two form is given by a polarization. So it's just some pullback of some two form here. And this pullback, it's a two form. And Hein proved that this is actually a 1-1 form, which is semi-positive. The proof itself is not very complicated, but there's one very important thing which is behind this, is the so-called Greenfield's transversality. Even though this is not an abelian variety, when you pull back to S, it's still semi-positive. It's very important that you pull back to S. So this is still a semi-positive 1-1 form. On the other hand, this local system of real tori defines a foliation, and then you can define the so-called Betti strata or Betti locus. So this is exactly the loci on S such that it intersects the leaves non-trivially, non-discretely. And you see, because this Betti form is the pullback of this one along this foliation, so you see immediately that this top wedge power is not identically zero. It is identically zero if and only if this one is the whole thing. So what we proved is, that this Betti stratum is Zariski closed, and we give a checkable criterion for it to be the whole thing. And next we're going to apply this one. The proof, is basically the same as I did for abelian schemes, but here the new thing is we need to use O-minimality for period maps to use definable Chow. It's no longer the Shimura world. This is by Baker, Klingler, Zimmermann, and Blumenbach. And another key point is the functional transcendence result, and this is mixed triangle. It's used twice, and once through the so-called geometric tuber pink, proved by many people. Okay, so now this is our goal, and we show that this curvature form is exactly the Betti form. So now we have our corollary. First of all, this Betti form is non-negative. This is Hein's result. And secondly, the top wedge power is non-zero. This is a corollary of this second part. And third, this Betti stratum is Zariski closed. The second one is this one for this particular case is also proved by Hein using a completely different method. The advantage of our method is it also shows the third part, the Zariski closeness, and it works for any family. But the advantage of Hein's method, it's more hopeful to compute this Betti strata in this particular case. Yeah, so each one has its own advantage. Okay, so now with all these things, we prove our main result. And the open questions are, well, first open question is, I think, in my opinion, this is the most important one. Can we really determine this endpoint locus? Given any curve, can you really compute that? And then the neftness result. The neftness, so this neftness is possibly, I think it might be able to be done. This one is really just the actual positivity of the Beilinson-Bloch height. And in my opinion, the neftness is even harder than the bigness. In the sense that if you can prove neftness, from neftness to bigness, I think, in my opinion, it's easier than proving the neftness. So you see, this is really, really hard. It's not like a Beilinson scheme, the neftness is given for free, basically. And next is, can we show that all the point Ceresa cycles are non-Gaussian? Currently, it's known for non-cubar points, but of course, we as arithmetic geometers, at least I think most of us care more about algebraic points. So it would be great if this can be done for also algebraic points. Yeah, and also, of course, for other families, but for other families, whether you can do this for other families. Okay, I think I need to stop here.
Thank you. Thank you very much. Questions, remarks?
No, sorry. What's the conjectural empty amp?
I think 1G equals 4, I guess Shouwu wrote a conjecture, which I don't exactly remember. One is the intersection of a quartic and a degree 4 and a degree 3 and a degree 4 thing. I don't remember. If you like, you can watch the video of his talk at the UNO conference at the HES. He wrote a conjecture when G equals 3 or G equals 4, but I don't really remember.
Not just the hyperelliptic.
No, not at all. No. It's never conjectured to be just a hyperelliptic locus. Yeah. Yeah. Right. So the thing is, if you have any family where these cycles are identically torsion, it's a torsion section, it must be contained in this complement. It must be contained in this complement. And many people have to have examples like Laga-Schnittmann, Wei Zhang, and Congling Qiu, and so on. Yeah.
Thanks, Ziyang. So to compute MG amp, you need more than just an effective geometric silver pink?
A lot more than that. A lot more than that.
Yeah. So there's some arithmetic.
Yes. It's really arithmetic or geometric, depending on how you see it. Yeah.
And just to understand though that your variation is pure.
It depends on how you see.
Okay.
Yeah. Well, in the proof of this one, of course, we use a mixed variation.
Okay.
Yeah. All right.
Wait.
I didn't understand why you emphasized that it be defined over Q as opposed to over a number field.
Yeah. Well. It's more the nature of this question. The problem is, even if you want to prove that it's defined over Q bar, it's very hard. So a priori, if you just look at the Betti stratum, there's no reason it's defined over Q bar. And in the construction is more hard theoretic in this setting. Even in that case, it's not known at all beyond the Shimura world. So some partial results were proved by Urbani, Klingler, and Ostava. So they proved that some part is defined over Q bar, but in practice it cannot be applied to any family basically. So for us, because we proved everything using this volume identity and automorphism of C, it turns out that it's moreover defined over Q, and it is really better because, again, for these cycles questions, so we do care about more about what number field that we want. Like mg is defined over q, so we do want this stratum is also to be to be also over q. It's really rational.
There are no more questions. We thank the speaker again.